Okay, all right. So we'll first start with maybe the course logistics, and then we'll get into the course. I have a meeting at 9, so we will cut short today's class by 15 minutes, but I'll make up for it tomorrow. Okay. So, what are your courses for this semester? For your first year, first semester MS in bioengineering? Is this course called Applied Linear Algebra and Data Analysis. This is a course that is often very well remembered by students. I've been teaching it for maybe 7 years now, for various reasons, but unfortunately for the wrong reasons. People often struggle with the course, at least initially. I think but in the end, I think if you put enough effort, it's really a subject that is very beautiful and fun to learn. We'll look into what we will do in the course a little later, but before that, so we will have so the course information or all the information that you require about the course is on my GitHub repository. We will send you the link to this. So if you go to this page, all the information you need is here. So yes, yeah. Sorry, let me share it. Right. Can you see the screen now? Yeah. Okay. So this is the course page. All the information that you need for the course will be here. The lecture notes, we are recording the videos, lecture videos, assignments, the submission link for assignments and all that. And we have 3 TAs for this course this semester, Parbati, Nilakshi and Sujit. So if you have any questions, you can always talk to them or come to me to clarify. Okay. So the course information, of course, is there. That's what I was showing you earlier. Right. It has some brief information about what the course is about, and then essential course content. So we will have in-class lectures. Even though we are streaming it, I highly recommend that you attend in person. Okay. There will be the scoring for the course will essentially include the assignments. Quizzes, you will also see that the midterm. In fact, we won't have a single midterm, we'll have 3 and we'll quickly take the average of the 3. And the final exam. Okay. For the assignments, most of them will be pen and paper. There'll be a substantial amount of programming assignments as well. There are deadlines for the assignment, and you are allowed overall 5 days that you can miss cumulatively. If there are 5, you can miss 5 assignments. Submit 5 assignments 1 day late. You can use up those 5 assignments. So please do not compose and ask us for an extension, because we've given you this leeway to because of unforeseeable reasons. Okay. Discuss among your classmates or with the PAs and stuff, things that you don't understand, but write the answers yourself. Okay. Do not just copy paste what from somebody else. If you have found that you're copying or plagiarizing, you essentially change the course immediately. Discussion is very good for you if you discuss it with your peers and with others. So don't copy paste. When you write it yourself, your learning is a little bit better. Okay? So I would strongly recommend to not do that. I also list some resources that you will need for the course. Don't just rely on the course slides. I have notes as well, which is incomplete, but you can look at that. But you should also go back to some of the books I've listed here, or go and look at lectures by Gilbert Strang and Stephen Boyd as well. Okay? Those are some very good lectures on linear algebra. Okay? That was most of what I wanted to say. Let's just look at the rough schedule. So we stop today. We should end classes by by the second or third week of November, and the 27th is when we have the final. I've roughly listed the dates when we will cover different modules, and if you can see there are 3 midterms. Each one of them might be a half an hour exam, and we'll essentially then take the average of the 3. Okay, so we will cover a good bit of theory, and every now and then, after we've covered sufficient amount of theory, we will then have a lecture on the application of whatever you covered so far and where these ideas get actually applied. So those lectures are essentially called application, so we should so those are maybe interesting for you to see where some of these ideas get actually used. Right? And then we have a schedule for the assignments as well. So we don't have to submit assignments for each module. They're all put together. The first 3 are due on 25th of August, next on 15th of September, and so on and so forth. Okay. And one thing I would suggest is already start looking at the assignments. Okay. Don't wait till maybe the 20th to say, okay, I'm going to sit and do the assignments now. So my suggestion would be, if you put in at least an hour of work every day, the benefits that you read from this course will be quite good. It is not a subject where you can sit the last week before exams and then just try and get through it. I don't think it's possible. Okay, that is most of what I wanted to say about the course logistics itself. I don't think I've missed anything else for now. If there are any questions, we can talk about them now before we move on to the course. But if there are any questions from people online as well, please let me know. Are there any questions? No, don't feel shy. Just ask away. No problem. No? Okay, all right, sure. Okay, then we'll get started and see what this course is about. Again, as I said, the lecture slides for each of these modules is available on the course page. So if you go click, then you should see the lecture slides. Okay. The first thing we'll do, which is probably most of what we will do today, is essentially an introduction to what this course is about, why you should do this course. You have to do this course, but in case somebody else for whom it's optional, why I think you should at least study this material. Okay. How many of you have had linear algebra in your undergrad? Among the 3 of you? You have? Okay. Which year was this in? First year, is it? Okay. Do you remember what all they covered? Roughly? Okay. Rank of a matrix, matrix multiplication, inverses. What else did they cover? What do you remember? Okay. What's in your first year maths course, is it? What about in your second, third, and fourth year, in your engineering courses? Did they cover linear algebra? No. What about you? Same, is it? Second year? In maths or in mechanical engineering? No. Maths or mechanical engineering? It was a mathematics course. Okay? And essentially, same thing as what they covered. How did they define the rank of a matrix? Do you remember? Roughly? Was it involving minors? The minor of a matrix? Okay, sure, see, that was my experience as well. Unfortunately, more than 20 years back, that linear algebra was essentially a small module in my first year maths course. And that's it. I never saw linear algebra after that in my engineering 4 years of engineering, which I think is unfortunate because the usefulness of linear algebra is immense. Okay? This I only realized later on after my undergrad. And that's one of the reasons why I thought we should do this in bioengineering, because linear algebra, as we'll see later, is actually a lot easier than calculus, and maybe right now has a lot more applications, but it's something I think that should be learned before calculus itself, and that's what Gilbert's plan also says. The linear algebra is more fundamental than calculus, right? And this course is essentially well, it started as a course on linear systems, where we did linear algebra and then linear analytical systems. And then it evolved into having probability and optimization, and it's evolved again for this semester into a course on linear algebra, probability theory, and an application of linear algebra and probability theory, which is linear regression. The reason I decided to include linear regression is because if you're working in medicine, linear algebra is something that is very commonly used for several applications in medicine. And a good understanding of linear regression is actually quite handy for many things. If you want to do machine learning and stuff, understanding linear algebra is actually quite helpful. Okay? So that's what we will do. So we will look at 3 things this semester, in this course: linear algebra, basic probability theory, and an application of those two in building, understanding, and interpreting linear regression models. Okay. And motivation for all this is essentially this. Most phenomenon or systems that we deal with in the real world is multidimensional. And what I mean by that is you have systems of phenomena that have multiple degrees of freedom, various ways in which they can change, or you could have, for example, disease conditions that have different types of causes and different types of effects. You often, when you're measuring phenomenon, you're not just measuring one variable, you're often measuring multiple things. Right? For example, when you go for a medical exam, they're asking you to do multiple tests. So you're essentially using multiple pieces of information almost always. It's never one single measurement that you're relying on. Okay? So you are essentially dealing with multiple variables at the same time, whether in engineering, science, any of those fields. Right? So being able to deal with this multi-dimensional data and multiple data is important because the world is multi-dimensional. There are different dimensions to how the world behaves. Right? And if you look at traditional undergraduate engineering, right, most courses, this was the case 24 years back for me. It looks like it was the same for you, maybe recently also, are still primarily focused on single input, single output systems, where you have one input and you're only looking at one output. Okay? Which is okay, that's how you start. You of course need to understand single input, single output very well before you can talk about multiple inputs. But then again, this is mostly not, the point I'm trying to make is that this is mostly not covered. Okay? Something weird is going on. For example, many of you would have studied Fourier, Laplace, Z transform and all that, and most of these is, again, primarily looking at systems that are single input, single output. If you've done a course on control systems or sequencing systems, you're essentially only then again looking at, even if you're looking at a linear time invariant system, you're looking at systems with one input and one output. Okay? And in mechanical engineering, if you've studied dynamics, there also you've probably done courses looking at dynamics of systems with a single degree of freedom, for example, maybe a simple pendulum. Maybe most of these courses are unlikely to cover multidimensional dynamics, for example, dynamics of a multi-link robotic arm or something like that. So what I'm trying to say is in undergrad engineering, we don't cover many of these, even though it's something that should be covered. Right? So from your undergrad engineering, you essentially don't have all the tools to be able to deal with systems with multiple inputs and multiple outputs. Right? And it turns out that you need a slightly different set of mathematical tools. to be able to deal with systems with multiple degrees of freedom or systems that are multidimensional. And that is essentially where linear algebra comes in. It's really a first step towards thinking in higher dimensions. Okay. So, and that is where linear algebra features into this entire arena and why it's that useful. So I need to figure out what is going on here. It's interpreting my writing. I don't want it to do that. That A is the problem, I think, right? Yeah, right, yeah. I got it. Yeah, it should be okay now. Okay. Right. So the first thing is the world is multidimensional. We are confronted with multiple things at the same time, so we need to have a way of dealing with them. The second is the world is also uncertain, right? There are very few phenomena where you know something for sure, right? There is always some uncertainty associated with it, right? That's what I mean by saying the world is noisy or uncertain. Almost all measurements are corrupted by unwanted sources, which we might or might not be aware of. Okay, that means the outcomes and the outcomes of any action that you take. For example, I have a disease condition and given a treatment. The treatment is not the outcome of the treatment is not always certain. Right? There is a probability that I will get better. There is also a probability that I won't respond to that medication. Right? So that uncertainty exists. So many of the, not only are our measurements it's not just our measurements that have noise. Our actions also sometimes don't produce only the same output. That means the effect produced by an action is also uncertain. Right? There is some uncertainty associated with what will happen. Right? But just because it's uncertain, it turns out that it does not mean that you essentially wash your hands and say, okay, I'm done. I can't do anything because it's uncertain. It turns out that even though it's uncertain, there is some structure to this uncertainty. That's essential, and we can exploit the structure to essentially then be able to deal with the situation as effectively as possible. Okay? And the tools for doing that is again different from, or there are a different set of tools from what we studied in undergraduate engineering, where most of the systems we've dealt with is probably all deterministic. You probably had a course on probability, or maybe even some course in signal processing that deals with probability to it. Have you? Okay. What about you, Jerome? Mechanical engineering? Again, part of maths. Or was it a separate course, probability and statistics? So you've had a course on that, right? So it turns out we need tools from probability and statistics to do this. And that's also something that we will look at in this course, right? And so effectively the three major topics that we will cover is linear algebra, which is essentially the first step towards high-dimensional thinking, probability theory, an approach, a systematic approach to deal with uncertainty in the world, and a nice marriage between these two areas is linear regression, which is essentially a fundamental tool for modeling, for looking at relationship between variables, predicting using some of the variables and things like that. So those are the three topics we'll cover. And I'll simply give talk briefly about linear algebra probability theory as part of this introduction. So there is this book called All Mathematics You Missed by Thomas Garrity. There, in the first or second chapter on linear algebra, he makes this statement. He says, though a bit of exaggeration, it can be said that all mathematical problems can be solved only if it can be reduced to a calculation in linear algebra. So it turns out linear algebra is extremely fundamental even in pure maths. Right? And here, we all know what algebra means. We've studied it since our maybe 5th, 6th standard. So algebra essentially means the study of variables and the rules for manipulating them. We've seen this in trying when we study maths. And when we're talking about linear algebra, we're essentially talking about dealing with systems of equations like this. Okay? This again is something that we are familiar with. Right? All of us have solved equations like this. You know how to solve them. Right? This is in two variables. But if I give you 10 variables, you still know the principle that you can use to solve this. Or you can figure out, as you're solving the problem, you can figure out whether you can solve it or not solve it, whether there's a unique solution, infinitely many solutions and all that. Right? So we've seen this before. The linear algebra is essentially this. It's essentially the study of a system of simultaneous linear equations. I've written the two equation case here. What I've written down here is a generalization of that, where here x and y are the unknown variables. Okay? They are x1, x2, x3, xn here. So these equations have n unknown variables. And we have n equations. So 1, 2, n equations. Right? So the x's are unknowns, the a's and the y's are known, and we want to essentially now solve this and find out what are the values of x. Right? That's essentially the core of linear algebra. It's study of systems of equations like this. It's tedious to write a system of equations like this. You don't want to be repeating the same. If you need to write this multiple times, it's not convenient to keep writing these in this expanded form all the time. It turns out that there is another way to express this using matrices and vectors. That's essentially this. And we will see how to do this as part of the course itself, right? So this set of equations can now be written as a matrix multiplied by a column vector equals a column vector. A and y are known, where x is unknown. Okay. And depending on the context of the problem that you're working on, you might give specific names for x's, y's, and the a's. If you're dealing with, let's say, a problem of estimating something, then you might call your x's as the parameters associated with the system, parameters that you want to estimate about the system, and then your y's become would essentially be the measurements that you're making. You make some measurements, and from that you want to figure out the unknown variables of the parameters associated with the system. If you're dealing with a control theory problem, you have a system, you have a bunch of inputs. So you have a system, you have a bunch of inputs, and you have a bunch of outputs. The inputs are your x, the outputs are your y, okay? And input and output are related by this matrix A. In the control problem, you say, well, I want my output to be some value, some desired value, right? What inputs should I use to be able to generate that output? Right? So in the control problem, your x's would be called inputs, and y would be called outputs. And in both of these problems, A is simply something that relates x and y, right? And this is often called the physics of the problem. If it's an estimation problem, it tells you how the parameters impact the measurements. If it's a control problem, it tells you how the inputs impact the output of the system. Okay? And well, you could say, well, I've studied all this in my first or sixth standard. Why are we looking at this now? Right? It turns out, okay, we know one way of solving this system of equation and figuring out whether it has a solution, or if it has a solution, is it unique? And if it's unique, how do I find that out? Okay? And what we looked at was just a mechanical way of computing the output. Maybe you've also looked at this problem geometrically, where you say, well, the first equation is the equation of a line in 2 dimensions. The second equation is another line. If you're asking about what is the solution, you're essentially asking where do these 2 lines intersect. Okay. So you've probably done till there, right? It turns out that you can look at this a little deeper. Okay. And when you have simple equations in 2 dimensions, there are 2 unknown variables. It's easy to visualize and work with them, and easy to solve them by hand, right? But in real world application, it turns out you would be dealing with problems where there are thousands, there are hundreds of thousands of unknowns, hundreds of thousands of measurements, or even more, and humongous matrices A that essentially relate to unknowns and measurements or outputs. Okay? So linear algebra essentially gives you a deeper look into Ax equals y, and allowing us to get a better understanding of what is understanding of the problem itself, and to look at ways of manipulating your problem, simplifying it and things like that, and efficiently solving x equals y, right? And all you're doing in this is essentially solving x equals y. Okay. And you're just going a little deeper to gain a better understanding of the problem itself through the tools of linear algebra. Okay. We will also look at probability theory. This is essentially a branch of mathematics dealing with probability, which is essentially a measure of uncertainty. All of us know this, right? So, and probability theory essentially gives you tools for representing, analyzing, and manipulating events with uncertainty. Essentially, how do you manipulate probabilities of events? If I know probabilities of X events that happen, from this, how do I compute the probability of another event which is related to these events, and things like that. And some of the essential concepts we will cover is to look at what are probability distributions, what are random variables, what is expectation variance, covariance, conditional probability, Bayes theorem, and all that. Okay, those are all topics that we will cover, which are really essential for core of probability theory. So, and we will also spend a little bit of time looking at the special distribution called the Gaussian or normal distribution, which is often something that we come across in statistics. So you can think of when you're doing systems theory, linearity or linear system is something that we commonly look at. You can think of the Gaussian or the normal distribution as the equivalent of linearity in probability theory. Okay. And just with these two areas, right, if you have a good handle on linear algebra and a good handle on probability theory, it turns out you can already do a lot of useful things with it in engineering and other fields, right? For example, just linear algebra and probability theory have applications in all of these fields that I've listed here. Signal processing, control theory, robotics, and so on and so forth. Right? We look at some examples now from some of these areas. For example, if you're talking about signal processing, right? In signal processing, we're dealing with time series. Let's say we're dealing only with time sequence. Time series that carry some information, right? Often, if when you're recording this information, you're recording things as a function of time. For example, if you're doing ECG recording, it's being recorded on, let's say, on a computer, right? And it's stored as a function of time. And if somebody asks you, can I visualize the ECG? What you might do is simply then plot it like this as a function of time, right? It turns out visualizing or thinking about a signal as a function of time, where time is independent variable, is one way of looking at the signal. Turns out there are other ways of looking at the signal which might give you insights that you might not see from a pure time domain signal. Okay? I'll give you an example. So here I've drawn a sinusoidal signal. And if I were to ask you to write the mathematical expression for this, you'd write something like this: A equals sine omega t. This you should be familiar with, right? And for any sinusoid, right, so you have the time record of the sinusoid, right? But to convey the signal to me, for example, if you want to convey that the sinusoidal signal information to me, you don't have to send me the entire time record. Okay? You only have to give me 3 parameters. If you give me those 3 parameters, then I will know exactly what sinusoid you're talking about, right? What are the 3 parameters? The amplitude, the frequency, and the phase, right? The thing is, for this particular signal, a sinusoid, you only need these 3 parameters to be able to convey that information to somebody else, right? Now the question is, okay, how do I get that information? If I give you a sinus time signal, and I ask you to extract the amplitude, phase, and frequency, right? So if I give you this, you know how to do this, right? You'll then take, maybe you plot this on a computer or on a graph paper. You then find out this distance. That's the time period. From this you can get omega, right? So if you want the amplitude, then you'll essentially then compute this time, and you'll say, okay, that's the amplitude, that's A. So you've got A and omega. And if you wanted phi, then you ask, well, where is time 0? Time 0 here. And then you then measure how much off my sinusoidal signal is with respect to 0, and then from that you compute psi. Okay. So if you have this, then you can, if you have the time profile, then you can do this manually. Okay. It turns out you can extract this information through another procedure. Okay. Instead of doing it manually. Okay. And this information about amplitude, frequency, and phase can be obtained by what is called Fourier transform. This is again something all of you must be familiar with, right? If you take this, if you do this transform of the time domain signal into the Fourier domain, the signal that looks like this periodic oscillating smooth signal looks like this, what I've drawn there, this signal. Okay, it's 0 for all. I've drawn f, that is frequency. The signal is 0 for all frequency except for some frequency here, which looks like it's 0.5, and it's got some amplitude there. So it turns out, if you look at this spike here, right, the location of the spike, the height of the spike, and the phase associated with the spike will actually tell you a omega n phi. Okay. So Fourier transform gives you a way of automatically finding out what is the, if you give me a time domain signal, what is the frequency, what is amplitude, what is the phase. Okay. If I change the frequency or the amplitude, it turns out the corresponding Fourier transform also changes. Okay. And it turns out Fourier transform is essentially a linear transform, and you can understand it through linear algebra. Okay. And all that is happening in the background, okay, is essentially something like this. Whenever most transformations that we deal with in signal processing will essentially have this form, where you have some time domain signal and or some unknown shape, okay, some arbitrary shape. Okay. Most transforms that we come across in signal processing, Fourier, Laplace, Z, wavelets, all of them essentially have this underlying structure. You have the time domain signal, and all you're trying to do is represent this time domain signal in terms of a few other known signals or signals of interest to you. Called phi 1, phi 2, phi n. So you could have, this could be infinite as well. You could have phi 1 to phi infinity, infinite number of signals that are of interest to you or signals that you like. And you're asking, well, can I represent any time domain signal as a scaled version of each of my signals of interest, where your signals of interest are essentially the phi I. And it turns out when you're doing Fourier transform, these phi i's are essentially signals like this, sinusoids of different frequencies. If you're doing wavelet, then each of these is a wavelet transform. If you're doing Laplace, then each of these is a signal like this. Exponential sinusoids. Okay, so all of these transforms actually are again can be in principle thought of as you doing something like this. Okay, here your y is your x of t, your arbitrary signal of interest. This a is essentially your phi i's, or a contains information about your phi i's, and this x are your c's here. Okay. And the equivalent here is, this is your x of t, and this blue spike that you see this blue signal that you see, these are your CI. Okay, and these two are related by word A, which essentially is a matrix containing sinusoids of different frequency. Okay, so don't worry too much if then you're not able to visualize it clearly. These are things that we will cover later on in the course. So you have your original signal X, and then you have your CI. It turns out X of t and CIs represent the same signal. It's just they represented in two different they represented in two different ways. That's all. Okay. Again, if you must be familiar with decimal and hexadecimal representation of numbers, right? If I have the number 15, right? Okay. this 1/5 that I've written down is a representation of 15 in the decimal notation. What is the corresponding representation in hexadecimal? Remember? Yeah. F. So in hexadecimal, you write it as F. I'll remove it. Both of them represent the same underlying entity, the count of 15, but the way they are represented is different. So you can think of it similarly here. Your time domain signal, these two represent the same signal, it's just you're looking at it from a different perspective. That's it. And linear algebra can be used for looking at something from different perspectives. And that's where linear algebra comes in signal tests. Right? Before we conclude, if you're just to convince you that about this, here you're probably thinking, well, I can just measure this. Why do I need some complex transform to do this? So this is okay for a pure sinusoid. What if I had a sum of sinusoids like this? Here I ask you, what are the different frequencies present? What are their amplitudes and what are their frequencies? There is no way you can do it manually. You can't take a ruler and then compute this. But if you do the Fourier transform, right, then you see a signal like this, and from this you can clearly figure out. You can say, well, there are 4 different frequencies that I see, okay, and each one has a different amplitude and phase. And this you obtain by simply doing your Fourier transform. Or you're choosing an appropriate A, which corresponds to you performing a Fourier transform. Okay. This is for time. You can also do the same thing with image as well. Okay. In quantum theory, again, the simple example that I could think of is a spacecraft. It's got 6 degrees of freedom, and there are lots of different sensors that are measuring its position and orientation. How do I use that information to know where my satellite is? And there are different actuators in the spacecraft, and how do I use them to essentially correct for its errors in orientation and position, or to move to where I want to move my satellite. So here again, you're dealing with multiple inputs, multiple measurements. From that, you have to figure out where my satellite is, and then you have to then decide, well, my satellite is here, I need to go there. I need to control these multiple inputs to move my satellite there. A typical example of having to deal with multiple pieces of information and multiple inputs that you need to control to be able to do something you want to do. Okay? An example that is closer to our field is maybe in robotics. Right? Most interesting robots have multiple degrees of freedom, and each degree of freedom is controlled by an actuator. Right? So I'm showing 2 examples of where robots are used in medicine, in rehab or in surgery. So in all these cases, we're essentially dealing with a robot, something with multiple degrees of freedom, with multiple sensors and multiple actuators. Your goal is to figure out where is my robot, what is the state of my environment, and how do I control the behavior of my robot so that it does what it's supposed to do. A typical example of system with multiple inputs, multiple outputs. Here again, linear algebra becomes vital. See, robots are highly non-linear. Okay? But it turns out linear algebra and linearized version of their behavior is still quite useful, both for control and for estimation. I'll just to give you a simple example. For example, if you have a 2-link arm like this, okay? This is a joint and this is another joint, and the robot can rotate about these 2 joints. Okay? Imagine your arm, shoulder, and this could be thought of as the shoulder. This is your elbow, and I can rotate my arm about the shoulder and elbow. And I want to figure out, if I give you the shoulder angle and the elbow angle, where is my hand? That is given by this equation. This is nonlinear. So, but we are dealing with multiple outputs and multiple inputs. The 2 inputs in this case are your joint angles. The output is essentially the XY position of my hand. Okay, assuming we are moving in a plane. So even though the position of the hand and the angular position of my joints are nonlinear, if you simply take the derivative of the position, okay, then you're essentially asking what is the endpoint velocity of my hand, okay, and how does it relate to the angular velocity of the shoulder and the angular velocity of the elbow. It turns out that problem is actually linear. Ax equals b. This is a, this is x, x. This is y. X equals y. Okay. Even though the joint kinematics is nonlinear, the velocity kinematics, or what is called differential kinematics, is actually linear. Okay. And this is often exploited. This linear structure is often exploited for different purposes in robotics. Okay. So here again, linear algebra fits in at specific places where it can be quite useful. Okay. Another area where both probability theory and linear algebra come into play is statistics, where the data that we often deal with is heterogeneous, high dimensional, and noisy. And statistics essentially provides you ways of representing this, evaluating relationship between variables, and building models for estimating different pieces of information and making inferences. Right? And in statistics, we use all of this. Probability calculus is also plays an important role, linear algebra, and also optimization to be able to accomplish these different things for dealing with data that is noisy, high dimensional, and heterogeneous. Okay. So there are different some application areas of linear algebra and probability theory. And the third part of this course that we will look at is essentially an application of both linear algebra and probability theory, and which is essentially the bread and butter of statistics, that is linear regression models. Okay? And when I say a linear regression model, I'm essentially talking about a model like this. Some variable y is related to variables x1, x2, xn, okay, in this particular form. Okay. And because we are dealing with measurements that are uncertain, there is also a noise term. Okay. And if you only look at this part, right, it is essentially a linear equation, right? Like the one that we saw earlier, right? And that means we are essentially dealing with something like this, like what I've written here, with some epsilon which represents some noise, right? So one way to think about this equation is, well, if I know the values of x1, x2 to xn, I can compute the value of y, provided that I know the betas. Okay. Right? So often what happens is y should be some health-related parameter that you're interested in, let's say health condition, right? Let's assume it's a continuous variable. Okay. X's are your different clinical tests that we're doing or that are performed on the subject and the information that is collected. We want to ask, how do the different clinical tests that I have, the outcomes from the clinical tests that I have, relate to this health condition that I'm interested in. Health condition is well, clinical tests are X, and they're related to each other through these betas, right? Often in these clinical tests, because you have a way of measuring the health status, we're now interested in finding out, okay, how is clinical test I related to health status? How strongly is it related? How is clinical test J related to health status? And things like that, right? And for the first step, or the first model that you want to build to relate these variables is usually a linear regression model, because it's the simplest model that you can think of. Right? And to be able to build that model, you need to be able to identify your betas. Right? And when you say you are fitting a linear regression model to a problem, you're essentially then talking about finding the values of beta. Okay? And that can be done through a procedure like this. Yeah. Maybe let's say 6 or 8 weeks into the class, maybe this expression here looks a little strange and maybe intimidating, but maybe 6 to 8 weeks from now, this should be something that you're comfortable with. You should say, okay, I know what that means. And this is essentially how you would fit linear regression model to say, okay, give me the set of betas that allows me to best estimate the health condition given my clinical tests. Okay? And that's what you're saying here. We want to minimize the mismatch between what My model tells me and what the truth is, and I want to find the betas that minimize this error. So, and when you pose the problem like this, the solution that you get, you actually have a nice analytical solution for data like this. There are other ways to pose this than what I've written down here. It just turns out, and they all have their utility. If you pose it differently, then the way you compute beta or the beta that you get will be slightly different. That's all. And the way you interpret them would also be different. And the place, and there are various places where linear regression models are quite useful. And I've listed some of them here. They're used for evaluating association between variables. So the sign and the magnitude of beta will tell you how x, for example, beta 2 will tell you how x2 is related to y. Okay, but with some caveats, we'll look at that later. Okay, they can be used for predicting. For example, if I have my x1 to xn, can I predict y? So you can use linear regression model for predicting something that you cannot measure, or it's very difficult to measure. So can I use something that I can easily measure and from that estimate parameter that is difficult for me to measure? So we're often interested in that. We're also interested in sometimes using it for extrapolating beyond what you have. I won't go into the details of this, but a simple example would be I've done a clinical trial of with let's say on a group of patients with different age groups, let's say from 18 to 60. This is the only group that I looked at. And I find that the treatment works well. And I've also found how well my treatment works as a function of age. Maybe the treatment works very well for, I've given a particular dosage of the treatment. And it turns out that for the given dosage, I find a relationship between outcome of the treatment and age. Let's say for a given dose, your treatment outcome is worse as you get older. Now you have a study that was done, and let's say it was published, evaluated study. Now you have a clinical case where you want to be able to apply this on patients who are 70 years or more older. Right? How can you use this result from the clinical study to be able to make a rational decision on how do we treat this patient? What dosage do we use to get a particular effect that we want? Right? One way you can do that is you have a linear regression model that tells you how effective the treatment is as a function of age. Maybe then you can extrapolate it from 60. You've only done from 18 to 60. You can extrapolate it to 70 and say, okay, this is what we should be doing. Based on the evidence that we have, this is the best thing that we can do. So that is another place where linear regression becomes useful. And the last one is causal inference. This is something we won't look at. Essentially looking at figuring out what is the cause of something. Okay? We're not only looking at correlation, but also trying to figure out is this something that really causes my variable to change. Okay? So those are different applications for linear regression, and to be able to understand, build, and interpret is actually quite a useful skill to have. I then quote from another book, Statistical Rethinking, where the author essentially says linear regression has a strong claim to be foundational. That means the most fundamental thing you can learn. Like linear models are the stepping stone towards understanding more general nonlinear models. Without understanding of linear models, understanding nonlinear models is really not that easy. Okay? And once you learn to build and interpret linear regression models, you can more easily move on to other types of regression which are less normal. Right? And it turns out some of the things that you learn in fitting and interpreting linear regression models will also come in handy if you want to do machine learning and other sorts of things. Okay? So that's a very brief of what this course is about. Okay? Three things: linear algebra, probability theory, and linear regression. And by the end of this course, maybe you should keep this as a goal for yourself. Okay? These are the 4 things that you should say I'm comfortable with by the time December is here, by the end of this year. Sorry, there is a typo. So you should understand basically algebra. Okay? And there will be a strong emphasis on, even though we say algebra, the primary emphasis of the course is essentially more geometric. Okay? You should be able to look at x equals Why? Or if you should look at something like this, A transpose A transpose, I will be able to say what this means geometrically, not just the algebra. This is some combination of numbers, but we should be able to say what this means algebraically, geometrically. Okay, so you should be comfortable with that. You should be very comfortable with what are called linear squares methods. Okay, you should be comfortable with basic probability and statistics. And if you come across a problem where you need to fit a linear regression model, you should be able to do that comfortably with whatever software you want to use, whatever software you are comfortable with. We will emphasize on using Python, but if you want to use R, Julia, MATLAB, whatever you want, you can use. If you're able to do these four by the end of this semester, then you really gotten something out of this course, and I really hope that you do. And to be able to do that, because remember I earlier on said you need a different way of thinking. That often takes time. The thing is, in linear algebra, once you train yourself to see it differently, you realize, why the hell did I not get it earlier? But to be able to get that shift in your thinking requires a little bit of time. And initially, it might seem overwhelmingly complex, that you just don't see it. But if you stick with it, put in the effort, it turns out your brain then figures it out. Right? And often I say, you initially just do, even if you don't understand, and then over time, the doing essentially helps. So the doing and the effort is very important to be able to get the material. So that's all I wanted to say as to why you should do this course. We have another 15 minutes. We will move on to the first module. But before that, if there are any questions that you guys have, then we will talk about them now. And same for the online audience as well. If there is anything that you want to bring up or clarify, we can do that before we move on to the next module, or the first module of the course. Okay, it looks like there is nothing else. So okay. Yeah, so we started with linear algebra. See, linear algebra is really a very intuitive subject, not a very difficult subject, but getting started might be difficult. Okay? And often what I found with many areas of mathematics is the initial difficulty is in the strange definitions that you have to get used to. Okay? It's like learning a language. Till you get used to some basic vocabulary and how to put words together, you really have no idea how to speak or understand what's going on. That's the same with linear algebra. The first two modules are very dry and full of definitions that don't seem very fun when you start up with, but they are absolutely vital. You have to spend sufficient time to learn by heart these definitions, and even if you have to just blindly do it initially, that's fine. Just if there is a rule that you need to apply, you blindly apply. Okay. I mean, once you do it enough number of times, then hopefully it will start to make sense. Okay. So the first module that we will look at is essentially looking at concepts in what are called vector spaces. Okay. Okay. We'll start with what are vectors. Okay. Well, if I ask you now what is a vector, what would you say based on your whatever you've studied so far? What is a vector? You know, you don't have to be sure, it's a small group, so what is a vector? Sorry, you have to be louder. Sorry, variable is it? What did you say? Variable. Okay, all right. Well, from our physics, from what we studied in physics, been told that vectors are quantities that have a magnitude and a direction. Right? Mass is not a vector, but velocity is. Right? Mass does not have a direction. That's usually called a scalar. Whereas velocity is a vector. Okay. The vector that we will talk about here is slightly different and in fact and more general. Okay. For this course, whenever we say vector, right, we are simply talking about a list of numbers. Later on, we will generalize this. We will turn out functions are vectors as well. Images are vectors. Matrices are vectors. Okay? So we will come to that later. But for now, I would simply remember vectors as ordered, and not just a list of numbers, but an ordered list of numbers. Right? So, for example, we will often write them like this. Okay. In the column, okay, where the number on top is the first element of the vector, number below that is the second element, so on and so forth. So if you had a vector with n elements, we essentially have n numbers written down like this. Okay. Right? That's an ordered set of numbers, and we will often follow the convention that we will use lowercase letters for vectors, and they will be bold. Okay. If it's not bold, if you see a symbol like this, which is not bold, that means it's probably a scalar. The scalar is simply a single number. Okay. Right. Well, when you put as a thing, you say number, but what number? It could be just integers, it could be real numbers, it could be complex numbers, and whatever. Right? So, numbers that we will deal with will mostly be real numbers, and sometimes we will have to confront complex numbers. So, for now, we'll assume vectors will simply be an ordered list of numbers, which are either real or complex. So, in general, if you say complex, real numbers are included. So, let's say complex numbers. Right? But most of what we will see will essentially be just the real numbers. Okay. And we will always represent vectors by a lowercase bold symbol. And when we say a vector, it's in a column. Always remember vertical list of numbers. Okay. Then the order matters. Okay. Okay. If let's say we have, because when I write, I can't write bold, and I will often put an underscore in the bold vector. If there is no underscore, then you know it's a scalar. Okay. Let's say I have a vector V, right? Let's say it has n elements. Okay. The individual elements, we will often index them by an integer. Okay. So I have vector V. The first element of vector V, we will often write down V1. Okay. See, there is no underscore here. That means it's not a vector. It's a scalar. And when we write down in the slide, we will see that the components are often not bold lowercase letters. Yeah. The second element would be V2. Right. So, for example, if V was a vector with 4 elements, then I would simply have V1, V2, V3, V4. That's it. Okay. And this is essentially the start of dealing with multidimensional stuff. Right. So, the individual numbers that you have could be the individual measurements that you get from your system. Let's say 4 clinical tests that you've done. The numbers V1 corresponds to clinical test 1, V2 corresponds to clinical test 2, 3 to clinical test 3, and so. The order matters because you can't mix the two. If for me, clinical test 1 is written down first, but for her, if you wrote clinical test is the 3 as the first number, then you've essentially now mixed up information. That's the problem. That's why the order matters. Okay. So the vector essentially, now you can think of it as a way of representing high dimensional information. Okay. Okay. That means if you have a patient from whom you're measuring multiple things, you can associate a vector V with that patient, right? That vector V has all the clinical tests that they did. If you're dealing with a system that has multiple inputs, multiple outputs, then the input is a vector. The individual elements of that vector will have the different inputs that go into the system. The output would be another vector. Each of the outputs would be the different outputs corresponding to the system. Okay? In our previous case, the two-limb robotic arm. Okay? Theta 2, theta 3, this is x comma y. If let's say the endpoint position of the hand was the output that of interest, and your joint angle was the input of interest, then the input would simply be a vector with two elements, theta 1 and theta 2. The output would be, let's say R, I call it R, essentially the x position and the y position of it. So vectors are simply a way of representing our multidimensional data. That's it. So it turns out that we can do some, or we can define some useful operations with vectors, essentially addition and not just a multiplication, but a scalar multiplication operation. And as I said before, most of what we will encounter, the numbers that we will encounter will be real or complex. Mostly real, but sometimes complex. Like this I've already covered before. The ith element of the vector V will be represented by Vi. Okay. And we now define what is called a dimension or size of a vector. Okay. Whenever I say dimension or size of a vector, it's simply the number of elements that the vector has. So if you have equals the size or dimension of this vector is 4. So that's 4 elements. Okay. In the robotics problem, the size of the input vector is 2, the size of the output vector is 2. Okay. Our dimension is 2. Okay. And let's say we are now dealing with a set of vectors that have n elements. Okay. And sometimes we will call them n vectors. So if you hear me say n vector, that essentially means it's a vector with n numbers. Okay. And if we know that we are only dealing with vectors where the individual elements are real numbers, then we will often write it like this. Okay. We'll say the vector V belongs to Rn. Okay, R power n. Okay. Where R is essentially the, what is this? Do you remember? What is this? What is the nice looking R, capital R? It's a set of real numbers. Okay, and what is it? Just a collection of elements, that's it, right? So this R is supposed to represent, imagine R as a bag, okay? And that bag has all possible real numbers. If you put your hand in and take out, you'll get a real number. That is for a single real number. When you put your hand in and take out, you get a single real number. N vectors, on the other hand, belong to this set called R power n. Essentially, n real numbers. Okay. Now, if you imagine this as another bag, okay, Rn as another bag, think of it as that big bag has n small real number bags inside. Okay. And if you put your hand inside and take out, you will always get n real numbers. That means you'll get an n vector. Okay. That's essentially what it means. And we will often write, if I say vector V belongs to Rn, I will write it like this. And this symbol here, strange looking E, this means you should read it as belongs to. Okay. All right. Now, you can talk about the equivalence between two vectors. We know what equivalence between two real number means. 1 equals 1. 1 is not equal to 2. Right? We can similarly talk about this equivalence operation between two vectors. But to be able to do that, you need to have two conditions. Okay? One, if you want to ask whether A equals B, we're asking this question. Right? The way you would evaluate this question is by testing two conditions. One, both the vectors must, sorry, it's a vector, so I should write this. Both the vectors must be equal in size or dimension. That means they have to be n vectors. Okay? And the individual elements have to be the same index wise. That means A and B, if both of them have to be n vectors. The first element of A should be equal to the first element of B. Second element of A should be equal to second element of B. And if it's satisfied for all n elements, then you say the two vectors are the same. They are equal. Right? This is another thing you need to remember. So the first two lectures, there is a lot of things you need to remember, but please make sure you remember them by the end of the lecture. That means tomorrow when you come back, you should know this. Otherwise, what happens is you are essentially lost. You don't know what equivalence means, so I make a statement, you're like, what does that really mean? And you don't understand. So please, at least for the first two lectures, it's better if you go back and review the lecture that day and make sure some of the definitions you remember. One thing maybe I should have done it here as well. One thing I've done for these slides is whenever there is something that you have to remember, I put it like this. So whenever you see this, make sure you remember it. So even if you don't understand why somebody is defining such a weird thing, just remember it. Okay? In fact, I should have done that for a couple of other things as well. For example, this. You should remember. So that's something you should remember. So tomorrow to ask you should be able to immediately tell me what that means. Okay. Okay. And we're going to stop here. It's already 8:45. And we'll take it from here from tomorrow. Okay. But just quickly review, remember the thing that we discussed so far. If there are any questions, then we can discuss it tomorrow. Okay. All right. Thank you.